This is a application support web page for materials and computational science softwares which are developed under NSM. So we have created for future support and help the people to get connected and develop the future software. So you have this summary page. We have created this discussion forum for any information, any things you want to share with the peer audience, then you can post it here. So we have this AMDKIIT. You can post your queries, suggestions, information here so that the others can have a look onto this. We have also created mailing list. So kindly join. We request all the members to join this mailing list. In future communication, we will be on this mailing list. MSCC application and NSM mailing list, AMDKIIT mailing list. Kindly subscribe to this mailing list. Any issues in using this software, you can always raise a ticket. The team here will provide you the best support. So kindly browse through this web page. All the information related to the software, support, further development in the software, community, everything will be available under this one umbrella. The training material we are going to upload on a YouTube channel. So the link is provided here. You can, after a week time, you can go through this link and you can see the recordings also. In closing, I want to emphasize that this workshop is not just about acquiring knowledge. It's about building community, bringing like-minded people together, further development and transformation in the area of materials and computational chemistry. I hope that you will leave here today feeling inspired, energized, and equipped with valuable insight and skill that you can apply in your studies and professional endeavors. Once again, thank you for being here, and let's make this workshop an unforgettable experience. Thank you so much. I request Professor Nishant Nair sir to start with the sessions. Over to you, sir. Thank you.
Hello, can you hear me?
Yes, sir. Yes, we can hear you.
Okay. Yeah. Good morning, everyone. Thank you so much, Ms. Agarwal, for introducing me and also introducing to AMDKIIT. And I really thank CDAC team to be very proactive in arranging this workshop. This is the second workshop that we are organizing on this, and really, deeply thankful to CDAC and helping us with all the aspects of getting the code really to the shape and conducting such workshops. So I welcome all of you to this workshop. I hope all of you can hear me.
Sir, sir, just a small.
Yeah, I'm going to share.
Shall we wait for 5 more minutes?
Sure. Yeah. Right. Yeah, we can wait.
Some more people, I think, may join by.
Sure, absolutely. Yeah. Let me try to share the screen by then, because there can be some problem. Yeah. So I may have to log out and log in because there is some reasons, some problems with the settings.
Okay.
You're able to see my screen, right?
Yes, sir.
Okay. Shall we start?
Yes, sir, we can start.
Okay, all right. Yeah, let me thank the CDAC team, all the CDAC team, especially Nisha Agrawal, to take the lead in arranging this workshop. And thank you all for your enthusiasm and sparing your time and joining this workshop. Um, myself, Nisham Nair, and I'm a professor at the Department of Chemistry, IIT Kanpur. And I am happy to say that we have developed this DFT program at our institute with the help of um, um, let me with the help of National Supercomputing Mission uh, and uh, and with the help of CDAC. And there are mainly three programmers or three developers for AMDKIIT. One is Dr. Paramita Ghosh, who is right now moved from IIT Kanpur to CDAC. She is also an active organizer, continuing as a developer of, I'm an organizer of this workshop and also a developer of AMDKIT. Sudhir Kumar Sahu, he's now a professor at IIT Dharwad, and he's no more working on this project, but he made some crucial contribution to this code. Then Ms. Ritamakar, who is currently my PhD student, who developed molecular dynamics code for AMDKIT and many other features that are yet to be released are under development by Ritamakar. So with this, maybe let me very briefly show you what I am planning for my lecture today. So I thought I will give you, because it's a tutorial come hands-on session, so I thought of showing you some very basics of density functional theory. Then I will introduce you to what is plane wave basis set, very
Excuse me,
briefly
sir.
about, yeah.
Sorry to interrupt you.
Yeah.
Your screen is not moving.
Ah, okay. Let me try it again. Now it's visible.
Yes, it's visible.
Let me stop sharing and share again. We'll share the entire window so that there is no. Now it's full
Yes, now
screen
it's fine.
actually. Yeah?
Yes, yes.
And is it
Yes, now
changing
it's
now?
fine. Yes,
Okay,
yes,
okay,
it's fine now.
okay. Right. So I was talking about the developers, and you can see the list of developers here. And the plan for the talk is that I will briefly introduce you to density functional theory, then plane wave basis set, then how do we do a minimization of structure, and very briefly about the ab initio molecular dynamics, which is kind of the core thing about AMDKit. Then, Paramita and her team, they're planning for demonstrating the AMD kit and also do a hands-on session with AMD kit. And finally, if there are some questions, that will be kind of discussed at the end of the workshop. That's the plan. So let me start with the basics of density functional theory. So how many of you have um, Uh, let me see the participants list. How many of you have actually used density functional theory till now? Can you raise hands? Okay, 4, 5, 25 people. You can click on the raise hands. There is a raise hands button. You can see here, right? You can see my screen. Okay. So, okay, all right. So there are non-zero number of people. Okay. So how many of you have learned, yeah, I mean, you can actually put your hands down. Click again on the raise button. I think it will put your hands down. Yeah. Okay. Thank you. So how about how many of you know the basics of DFT? I mean, have you learned it properly in a course or in a in a kind of a training program? Can you raise hands? Okay, right. Okay, good. Yeah. Okay, good, good, good. Fine. Thank you. Thank you so much. Yeah. Right. So not very many, almost 50% of the participants have used DFT for some applications that they have done. And some of you actually have learned also the basics. So, what's so exciting about DFT, right? I mean, especially physicists and chemists, they're kind of excited about DFT. So let's kind of figure it out, right? I mean, what's so exciting about it? So let me first of all introduce you what is a functional, because you see density functional theory, right? So what is density? Density is easy to, it's electron density, okay? The electron density is something, you can visualize as a cloud of electrons, right? I mean, that's the density of, so we'll define density properly later. Um, so functional, right? There is some term after density, functional. So what is functional, right? Function is something you are very familiar with. So what is a function? So function is let's say f of x is a function, right? So that f of x could be x squared. That's a function of x. Okay, so your argument is x, and the function f of x computes the value of the function for that given value of the argument. So for example, if I give 1 as the input, I'll get 1 square as the output, which is 1. If I give x as 2, then 2 square, which is 4, is the output, the value of the function, right? So the function simply computes x square for any arguments that's being given, right? So that means, um, so what you can see here is a number is given as an, so let me see, I'm not able to access my mouse. Hmm. The problem with the pointer is not coming, but you could see, or let me go here. Okay. Now you can see my mouse, isn't it? Right. Okay, so I'm giving number as an input as an argument, and what happens is the function evaluates that as an argument, and you get a number as an output, right? So one as an input, one as an output, number as an input, number as an output. So and that's calculated by the function, right? The output is calculated by the function. So 2 is a number, 4 is a number. Okay. Now the functional is slightly different. What you are giving as an input is not a number, but input is a function. Okay, so you're giving function as an input to the functional, and the output of that will be a number. Okay, so it's confusing. So let's look at a simple example. Let's look at this. F of x equals x squared, right? This is a function. Okay, f of x equals x squared, that's a function. This function f of x is the input to the functional, and this functional is in yellow color. You can see that is, this functional is integral 0 to 1 f of x dx. Okay, so what you do, you actually put x square here, evaluate this integral, and you get a number as an output. Right? See, you can see input is a function and output is a number. Okay, so this is actually a functional. All right, so that's what we are talking about is a density functional theory, which means a functional of density. So this is some some kind of a functional like this, whose input is a function. Okay, whatever is that function. Okay, and that will be entered to this functional, and it will give you as an output a number. Okay, that's what is the kind of the format in which density function theory is going to work. So we need to figure out what is that functional and what is that function. Okay, so of course you got a hint that density, electron density is involved in all this business. So how it is involved and what is this number which comes out of it, all of those we are going to see. Okay, I hope it's clear. Now let's look at the next slide. Let me give you some examples, real life examples of functionals. Okay. Okay. So anybody realize this first equation here on the top? Here in this one in yellow, anybody? What is that equation? Anyone? I can't see the hands raised, but you can just unmute yourself and say. Okay. You don't know? Okay. All right. You know H psi equals E psi? All of you? I hope you all know. H psi equal to E psi is something that you all know. So this is nothing other than psi star H psi is basically the energy. Okay. Right. So so psi star H psi is energy E, which is nothing other than the Schrodinger equation, right? So that functional. So this could be an example of a functional. Okay. And what is the input? Input is psi of x, the wave function of the problem. So you provide as an input the wave function. You evaluate this functional for the given psi of x. You will get the energy corresponding to the functional. Okay. So this is a wave function based functional that you're seeing. Okay, this functional h is a defined operator, mathematical operator, maybe one, maybe a derivative, maybe multiplication with a number, etc., etc. So this will operate on whatever is your input psi of x, and evaluate this whole quantity, and will give you as an output. Okay, so density functional theory is similar. Okay, you give input density. Okay, what you are entering is the density, and the output is the energy, which is a number, right? I mean, this is also a number, like we saw in the previous slide. The output has to be a number, input has to be a function, and this is a functional, right, on which you are going to enter the function. So rho of r is a function. You enter to the functional, you get the energy out. Okay. So this is what the whole story, that you give rho of r, which is the density, which is a function, right? This is a function of r. So what is this r? I'm going to tell you what r is. R is nothing other than x comma y comma z. Okay, Cartesian coordinates. The density is sitting on Cartesian space, x comma y comma z, like any, like an object sitting in space, it will have x, y, z coordinates. Same thing, density is sitting on in the three-dimensional space, Cartesian space, and it has the value of that density depends on x comma y comma z. So density is the function of x comma y comma z. Okay, that's the function that you are entering to this functional. Okay, and this functional will give you an output, and that output is a number like we discussed, and that's nothing other than the energy of the system. Okay, so what in density function theory we are doing is to formulate this f rho of r, which is the density functional, some functional of density. You can see here, this is again a functional of wave function. This is a very familiar equation for you, psi h psi. Okay, this is simply your Schrodinger equation, right? The same thing, can we formulate a functional like this whose input is density and the output is energy? Okay, so why are we trying like this, and why is it so exciting about density functional theory, or what makes it so popular is the fact that if you look at psi for n particles, okay, for n particles, the number of degrees of freedom, number of variables required for you to define the wave function is 4 into n. Okay, so which means, so for example, you have got three, you know, I mean, basically three electrons. Okay, so then what you're having is 4 into 3 degrees of freedom, which means 12 degrees of freedom to define the wave function of just three particles, three electrons. In this case, it is not dependent on, it is simply not dependent on the on actually the the number of particles. It is just a cumulative density. Okay, it's a cumulative density. it is simply depends on only x and y and z, the space, the point in space where you are going to talk about the density. So therefore, it only depends on 3 degrees of freedom, which is the Cartesian degrees of freedom, x, y, z. So which means there is a dramatic decrease in the number of degrees of freedom you need to define, the density over a wave function of n particles. So this is a huge reduction in the degrees of freedom. I mean, lesser the degrees of freedom, of course, easier will be to do any calculation, right? So that is what is so exciting about DFT. So all of you are with me? Okay. All right. Now let me define electronic density, because we said electron density is exciting. Okay. So let me see. Let me introduce you some exciting features of electron density. Okay. So what you see here on the top in yellow box is rho of R. I told you that R is nothing other. It's a vector in Cartesian space, which means it is simply x, y, and z. Okay. Okay. So rho of R. Okay, which means rho of x comma y comma z. Only 3 degrees of freedom. So I can of course write instead of R R1, which means x1, y1, z1. I mean, it doesn't matter. It's just a variable. Okay, so I'm going to rewrite rho of R as rho of R1. So, and how that density is defined is it is an integral. You can see it's an integral. It's a multi-integral. Okay, integral over as you see d omega 1 to d omega n, dr2 to drn. So those are the variables on which you are going to integrate this quantity. What is this quantity? This is the wave function of n quantum mechanical particles, in our case electrons. Okay, the wave function, the mode of the wave function square, okay, which is nothing other than probability density. Okay, that's the probability density of the wave function, and you are integrating out every coordinate other than the electronic coordinate of particle number 1. Okay, so this is the probability density integrated over all the coordinates except particle number 1, and therefore the quantity that you get is a function of, let me mute the person who is making noise. Okay. Yeah, so you can see this will be a function of electronic coordinate number 1. Why? Because you are not integrating out electronic coordinate 1. You are integrating out all other coordinates except the coordinate of electron number 1. So therefore, whatever you are getting is the probability density, the net probability density along the coordinate R1. Okay. So this is how you define the electron density. And the way you define this, you can see it's multiplied by n, and the reason why you are multiplying by n is to make sure that when you integrate over even the coordinate number 1, you get the total number of electron as an integral. Okay, if you integrate out or integrate the density over the entire space, you will get number of electrons as an output. So that's one property. So the number of electrons, if you know the electron density of a system, for example, this is the electron density of a water molecule. Okay, this is a water molecule. If you know this electron density, and you can get electron density from X-ray scattering. Okay, that's wonderful. So you can do experiments to get this electron density, possibly not as accurate as that we do that in theoretical calculations, but you can actually get this electron density. You do integral, you sum over all the space of that electron density, you will get the total number of electrons in your system. So this is a beautiful thing, because number of electrons per number of particles that you are talking about can be calculated directly out of the electron density. And another interesting property of electron density is that it falls down to zero as the distance is increasing, right? You can see as it is getting farther and farther from the nucleus, okay, you can see that the electron density is going to zero. Okay. So this is an electron density projected onto X and Y plane, right? Actually, electron density, as you can see, it's a function of X, Y, and Z. But I have integrated out the Z coordinate just to demonstrate you that you have such kind of a property. Okay. So now there is another interesting property of electron density is that wherever there is a nucleus, okay, or where the positions of the nuclei, you can see this is the position of oxygen, this is the position of hydrogen, this is the position of hydrogen, and you can immediately see that from this picture because there is a maximum, a finite maximum of electron density at the positions of nucleus. So which means the nucleus are sitting in space if in various Cartesian positions, Cartesian coordinates. And if I actually look at the property of the electron density, I see, oh, there is a maximum at that position for electron density. Then I immediately say, I know there is a nucleus there. Okay, so which means the position of the nucleus also can be predicted or can computed exactly if you know the electron density. Okay, so it's not only the number of electrons that you can calculate using this equation, but you can also find the position of the nuclei of your molecular system from the electron density. So you don't need to ask where the nuclei are, right? You give the electron density, you can immediately say, oh, that's where the nuclei are situated in the three-dimensional space. Now, another wonderful property of electron density is that there is something called a cusp, okay, at the position of the nucleus. Now, what is cusp? Cusp is where the gradient of the density has a discontinuity, okay. So there is some kind of a discontinuity in the slope of the density at the position of the nucleus. And interestingly, the property of this discontinuity depends on the nuclear charge. Okay, whether it is oxygen, whether it is hydrogen, whether it is nitrogen, depending on the nuclear charge, right? I mean, oxygen will have a different nuclear charge than nitrogen, will have a different nuclear charge than hydrogen. So that means if I actually measure the cusp, right, I can measure the cusp. There is no problem because I already know density as a function of x comma y comma z. So I can easily calculate the cusp. I just have to do a derivative, right? And look for the cusps, which means wherever are this discontinuity. And I actually look at this discontinuity, some property of this discontinuity directly relates to the nuclear charge, which means I can calculate the nuclear charge also knowing the electron density. Okay, so I know the number of nucleus, of course, because that is equivalent to the number of cusp. From the cusp, I can calculate the nuclear charge. I can predict the nuclear position. I can predict the number of electrons just by knowing the electron density, which is, I can, for example, I can get from X-ray scattering. Okay, and this electron density is simply a function of X, Y, and Z, just three-dimensional quantity. Okay, but it gives you so much of information. So this is wonderful. Why is it so wonderful? Because I will show you soon that that is all the information I need to solve a quantum mechanical problem. I don't need to know anything else. Okay, to solve the quantum mechanical problem, I just need to know only that. So therefore, I will be able to use density to solve quantum mechanical problem. So I'm going to come to that. Before that, I'm going to use certain expressions in the following lecture. So let me kind of slowly introduce you to that. And I just want to warn you that, this is such a short tour of density functional theory or short introduction to density functional theory that I won't be able to really go in great detail, but always you can reach out to us with questions and you can always look at the textbooks that we have given um, for learning more. Okay, so for example, this book of Cohen Holthausen on a chemist's guide to density functional theory is something that I highly recommend. Okay, so let's look at some of these notations I'm going to talk about. So to make the life simple, let me now go to 3 dimension. Let me look at 2 dimensions. Okay, so in 2 dimensional space, again, for the benefit of using the pointer, I'm going to go in escape mode. So you can see this is an electron density situated in 2 dimensions. Right now, we are not worried about 3 dimensions. We have only x and y. Okay. So now this is an electron density that is situated in 2 dimensions. This is in blue color, and the cusp, the position of the cusp are these small circles. Okay. So just by knowing the cusp, I know, oh, those are the positions of the nucleus. Okay. Now, in all my calculations, what I'm going to do is to look at the density on some grids. Okay, what is grid? Grid is simply a grid like this. Okay, so grids are defined, over its Cartesian position. So here x and y value, a specific value of x and y defines that grid. And what you can actually think of is having, a position vector defining the position of that grid. Okay, so this R1 will be simply x1, y1 that defines this grid. This R2 simply defines x2, y2 that defines this grid, and so on and so on. Okay. Now I am assuming that this density is simply a function of x and y for now, for the moment. In that case, integral dr rho of r, this integral is nothing other than sum over. I mean, this continuous integral can be simply written as a sum over all the grid points. You can see all these grid points, right? I mean, there are so many grid points, 1, 2, 3, 4, 5, 6, 7, so maybe 7 into 7, maybe 49 such grid points. So I'm going through one by one to individually to these grid points, and the density is situated on that grid point. You see, density is a function of that grid point. So each of these grid points will have its value of density, right? And multiplying by dr. What is dr? Dr is simply the volume of this pixel. Okay, so dx into dy. Dx, this is the width of the pixel. Okay, and dy, dx into dy, that gives you the volume element. You multiply by the volume element, sum over the entire space. What you're going to see is you're going to get the number n, which is the number of electrons, which means this density is nothing other than the number of electrons per unit volume. That's your electron density. Okay, so the number of electrons per unit volume, that's how that's how you have defined the electron density. So that when you actually do such, I mean, this sum is nothing other than this, right? You're going through one by one through all the grid points, looking for the value of the density, multiplying by the volume element, you will get the total number of electrons. Of course, now we will be never working on 2-dimensional space. We'll be looking in 3-dimensional space. So which means we will have a situation like this. We will have a 3-dimensional grid like this, okay? Where, instead of a 2-dimensional grid, not a pixel, but a voxel, okay? Where we have, this cubical pixels, okay? And within that small, volume in 3-dimensional space, we will be measuring that electron density, and that electron density at any point in this 3-dimensional space will give you the number of electrons per unit volume in that position. Okay, so that is the way we define electron density. I hope it's clear to all of you. Any questions till now? Okay, wonderful. Yeah.
Sir, please check the chat section also.
Sorry?
Sir, please check the chat section also. They're replying on the chat section.
Okay, I see. It's very difficult for me to see both. Okay, maybe I can take the questions in the chat.
Nothing important
later.
in the chat, sir. We will inform you
Okay.
once.
Right. Okay. All right. So now, so this is why now we have set the very basics. So now let us ask this question. I mean, can we really use electron density to predict total energy? right? I mean, that's the fundamental question. So if you look at what we just discussed, that if I know the electron density, I know the number of electrons, I know the position of the nucleus, I know the nuclear charge, okay, which means for any molecule that you think of, any molecule that you think, it could be hydrogen atom, it could be hydrogen molecule, it could be water, bulk water, it could be protein, it could be an RNA, it could be a membrane, it could be the whole virus, it doesn't matter. You know the position, you can, if you know the electron density, you can predict how many number of electrons are present, number of nucleus is present, number of charges is present, which means for that specific system where the total number of nucleus is fixed, the charges of the nucleus is fixed, the positions of the nucleus is fixed, you have a unique way to define Hamiltonian operator in quantum mechanics. Okay. Now, I cannot go very deep into the introduction of quantum mechanics, but you have to, if you are not familiar with it, you just believe that, okay, Hamiltonian operator, defining Hamiltonian operator is critical for you to solve Schrodinger equation. And we are going to have a shortcut of solving the Schrodinger equation using density. But what you really immediately see is that, okay, it makes really sense to that you should be able to predict energy of a molecular system, even if it is a virus or a hydrogen atom or I don't know, a hydrogen molecule, because you know all the variables, all the parameters required for you to define the Hamiltonian operator just by knowing the electron density. Okay. So therefore we are excited. So I mean, is there any way that we can actually give density as an input to a function so that we can predict the energy, because the density itself will uniquely define a Hamiltonian operator whose solution is the energy of the quantum mechanical problem. Okay, so that's the exciting thing about or I mean, we are kind of sure that what we are talking is not nonsense, because there should be a way to do it. The conventional way of taking the many particle wave function, okay, possibly is not needed, for the reason that the Hamiltonian operator is uniquely defined, and as I showed you earlier, that the number of degrees of freedom, number of variables that you need to handle when you deal with wave function is much larger than a density. Okay, and therefore it should in principle simplify the mathematical problem that we are looking at. Okay. So I mean, formally, this is first shown by Hohenberg and Kohn in 1964 with this legendary paper. The nice thing is that we are kind of celebrating the 60th year, right? I mean, with this paper, so which is really amazing that we are doing this kind of meeting also in this year. And so, I mean, I strongly recommend that all of you read this paper. This is possibly the easiest way to learn density functional theory, because it's almost written like a story, especially if you have some basic knowledge of mathematics. You will appreciate this paper very well, because it's possibly the best way density functional theory concepts can be written down. Okay. Now you can even read the title and then many I mean many things you can kind of understand. Okay, but wait till I introduce you to a little bit more of density functional theory in a couple of slides, then you get it even better. Okay, so the electronic Hamiltonian operator I was talking about, right? I mean, it actually has three main ingredients, right? One is actually it tells you how to calculate the kinetic energy of the electrons, because electrons are just moving around, and we simply assume that the nucleus is fixed and the electrons are simply moving around the nucleus. Okay, that's kind of the picture that we have. Later, I will move the nucleus also, but right now, for us, the nucleus are nailed in the space, and then the electrons are just moving around. So we need to measure the kinetic energy of electrons as it is moving around the fixed nucleus. We need to deal with electron-electron interaction because they're like charged particles. Okay, -1 e charge for each of these electrons. So therefore we have to introduce the potential energy of interaction between the electrons. Then of course nucleus is is positively charged and therefore electron is negatively charged. So there will be an attractive interaction between nucleus and electron, which also needs to be incorporated. So electron interaction is largely is repulsive. Nuclear electron is attractive. Then of course you have got kinetic energy. So the first part is the kinetic energy. Second two terms will be the potential energy, okay, part that we have to introduce. And also of course there are also nucleus interaction, but I am not, or we are not worried about it right now, and we will deal with that a little bit later when we deal with structure optimization or molecular dynamics, because that's when it becomes more important. Right now, since our nucleus is fixed in space, the nucleus interaction is simply a constant number, okay? Because it's simply the charge interaction. So therefore, I'm not including the nuclear interaction right now, but we will consider that a little bit later. Okay. Okay. So now to set the stage from especially following this Hohenberg and Kohn paper, what is so exciting about this paper is that it says that energy can be calculated as a functional of density, like we discussed earlier. Okay, it should be possible. Okay, and it is proving in this paper. Okay, the proof is given, and in that case, you can split this functional into two part. Okay, a functional which is what is called a universal functional, and the other is what is called an external potential functional. Okay, so functional of density again. So let me actually go in details. So this universal functional is something, it doesn't matter whether you're talking about helium, you are talking about nitrogen, you are talking about oxygen. It is universal. This functional form is simply universal. Okay, this is not a universal function. It depends on whether it is oxygen, hydrogen, nitrogen, what is actually the actual composition of your molecular system. So, and that is actually called an external potential. Okay, so you will realize why it is called external potential in a few slides. So this universal functional should contain the kinetic energy, right? Because the Hamiltonian operator should have these contributions. So it should somehow um, compute the kinetic energy of the electron, okay? And it should somehow compute the electron-electron interaction as well, okay? And their functional of electron density. So that should be then such a function should be existing. Okay? Now, uh, now, so So let us therefore write that since I know that these two are contribution, and the kinetic energy of electrons and electron-electron interaction should be contributing here to this functional. So let me kind of write it as the kinetic energy functional plus the electron-electron interaction functional. Okay, some functional form will be there, and together these two functional together forms the universal functional. And why is it called universal functional? Because they are not dependent on the specifics of the atoms that are present. Okay, it simply depends on that, in general, universally for anything. Okay, you just need to provide as an input the density. This functional together will give you kinetic energy plus uh, electron potential, okay, interaction potential. This one, on the other hand, is an external potential because it will depend on the nucleus, because it should therefore contain a nucleus electron interaction, right? This nucleus electron attractive interaction. And certainly when the nuclear electron attractive interaction, you can think of it's like an classical electrostatic interaction, Q1 Q2 by R kind of a potential, where the Q1 is the nuclear charge, right? So the nuclear charge is different for oxygen, is different for nitrogen, it's different for argon. So therefore, this external potential is certainly going to be dependent on the details of the atoms that are present. So therefore, this particular component of this energy functional, which you are developing, uh, should depends on the kind of atoms that you have. Okay? So we call it as external potential. Okay, so now what is another exciting part of this paper? This paper also tells you or prove you that energy functional is variational. The functional that you have devised is variational with electron density. Okay, now what is variational with electron density means? Which means let's assume that somebody gave you an electron density for this 3-atom molecule. Okay, so which is your row 1 of R. You can see that on the top of the screen, right? Okay, so that is the density that you got from somebody. Okay, so you have the energy function. Let's assume you already know the energy functional E row of R. Okay? You give an input, row 1 of R as an input, you get energy as an output. Okay, so that is what you see here, right? I mean, so this one is basically the energy of, let me move this. uh, so I've given row 1 as the input, which is this density, and I got an output, which is this energy. Okay, now I asked somebody else, then they said, no, this cannot be the density, this has to be the density. I said, okay, fine, I'll take your density, and I put it to the functional. Then I got another value of the energy. Okay, so now I'm confused, like, okay, what is the right density, right? So I keep asking more people. So somebody gave me row 3 of R, somebody gave me row 4 of R as the density. Okay, again, density is just a function of x comma y comma z, right? I mean, I'm just collecting it from various people, and I'm putting into this functional, and then as an output, I'm getting the energy, and then simply connecting all these output energies by some dotted lines. Now my question is, who is correct, right? Is 1 is correct, 2 is correct, 3 is correct, or 4 is correct? Then I can confidently say by looking at this plot, oh, 3 should be more close to the actual solution. Why? Because that gives you the lowest energy out of all that you tried. Okay, and that is what I am talking about, is the variational with respect to electron density, which means you change the electron density and you look for the energy. Okay, the best, the right density is the one with the lowest energy. Okay, you modify the density a little bit, the energy will increase. Okay, so the density for the ground state, or the lowest energy state, okay, can be easily figured out, because that is the one where even a slight disturbance in the density would cause increase in energy, and you can never come up with any value of density which can be lower than that energy of that system at that point. Okay, so in this case, we don't have all the information, we don't have any points between 2 and 3 and 3 and 4, so we are not completely confident here, because we at least we see that the actual solution, the actual ground state, the optimal density of that molecular system is close to row 3 of R, but but I can't be very sure, right? This is amazing. Actually, this is a great property. Why is it great property? Now I can actually start a calculation with some approximate density, a guess of the electron density, and then I use mathematical tricks, okay, to minimize that energy function. I keep modifying the density, okay, and I look for the minimum of the energy. Minimization, right? I mean, minimization is something that in mathematics you kind of learn, so not a problem for you, right? So you know how to minimize a function, right? So you can actually try to minimize the energy functional where you modify rho. Okay, so you change density. Rho is your variable. In fact, that's a function, but you modify the function. Okay, and you look for the output of E of rho of R, and try to see where it is the lowest, and that is the is the right electron density. of course, you will also predict the energy of your molecular system, because the row which gives you the lowest energy, that's the energy that you are looking for the molecular system. So you should be able to predict the energy of the molecular system just using this energy function, and this is mathematically proven in this paper. So that's the beauty of this paper. But it has never told, this paper is never going to tell you how you actually devise these functionals. What are these functionals? It only tells you the general features of the functional. It tells you what is the implication of this in terms of, in terms of theory. So right, so what we just now learned from this is you can have an energy functional, okay, and the exact density or the exact ground state electron density of any molecular system, okay, will have the lowest energy, and anything other than rho zero of R, which is the exact density, will have a higher, have a higher energy, okay, always. Now let us get into practical computation. How do we really do it? Okay. So let's right now let's not talk about kinetic energy, calculating kinetic energy of electrons using density, because that's a bit complicated. So I'll come to that in the next slide. But let's look at the two easy quantities. Okay. Electron-electron interaction, electron-electron interaction as a function of density, right? It's a functional that you're looking for, and of course the function that you are inputting is the density, right? So you need to express the electron-electron interaction in terms of density. Unfortunately, electrons that we deal with are quantum mechanical objects, so the exact electron interaction is is not exactly a functional of density, okay, but we can approximate it. We can say that, okay, so there are 2 points r1 and r2 in space. If I know the electron density as at point r1 and point r2, classical classical interaction, that classical repulsive interaction between point r1 and point r2 will be q1 q2 by r12, right? What is q1? Q1 is the number of electrons present at R1 into the charge of that electron. Okay, that will give you the total number of charge present at R1. Then you have R2 in space, and R2, okay, what is the total charge in R2? Remember, R1 is a pixel, R2 is a pixel, okay? So a position in the grid, but of course you are going to think of density situated in that pixel or a voxel. So then you have another point in space, which is R2, and you need to know the total charge at R2. So you take the density multiplied by E minus E, actually, you get the total charge at R2. Okay. So rho of R1 into minus of E into rho of R2 into minus of E divided by R12 into, of course, 1 by 4 pi epsilon 0 will give you the total electrostatic interaction of electrons at R1 and R2. Okay. But this is of course an approximation, because this is not the right energy, because these are quantum mechanical objects. So there are also quantum mechanical effects to it. It's not exactly this interaction. Okay. Here also you see that I'm going to sum over this interaction over in all the grid points, integral dr1, and the other integral is running over integral dr2. So I'll be also double counting those interactions, okay, because the same interaction r1 r2 will be also computed as r2 r1, so I'm double counting it, so therefore I'm introducing a half here. Okay. Now I told you initially that rho into minus of E, rho into minus of E, I mentioned that's a total charge. So E, you can see that E is simply not here. And I also told you 1 by 4 pi epsilon 0 is required. So none of that is here. The reason is that this expression that you are seeing here is in atomic units. In atomic units, E is 1, okay, and 1 by 4 pi epsilon 0 will also become 1. So therefore, you don't really see that in these atomic units, okay. So half integral dr1 dr2 rho of r1 rho of r2 by 1 by r2 is an approximate way to compute the electron-electron repulsion in atomic units. Okay, so this is okay. Okay, we have simply put a tag saying that, oh, I know this is approximate, I need to correct it. This is simply a classical interaction, like a classical system, but we have quantum mechanical objects, we have electronic spins, we need to worry about electronic spins. So we need to, there will be some difference in this electron-electron interaction because of the quantum mechanical nature of the electrons. Fine. Let's look at the next one, which is nucleus electron interaction. This nucleus electron interaction is trivial. Okay, why? Because I already know the electronic charge in space. Okay, I know the nuclear charge. Okay, which is Z, right? Which is Z, which means I have to calculate Q1, Q2 by R, isn't it? Right? So if Z into E is the charge of the nucleus, rho into minus of E is the charge of the electrons, then rho of R into Z into E by R1 Ri simply means the distance between the electronic grid at some space x comma y comma z to the nuclear position. Okay, will give you the Coulombic charge. Okay, and of course you have to sum over all the nuclear charges, and that gives you the total electronic interaction, the total electrostatic interaction between the nucleus and the electron. Okay, so this is a straightforward from classical electrostatic. Okay, we have this expression for nucleus electron interaction. Okay, this is simply Q1 Q2 by R. Okay, so I have put this term Ne in green color because that's tick. Now it's very clear. If I know the density, okay, I know how to calculate the nuclear charge. Okay, and of course you can see that functional is now very clearly defined. This functional is trivial. This is the functional form. Electron-electron, this is a simple functional form in terms of density, but the problem is that we know already this cannot be the accurate electron-electron interaction. Okay, so one part is done, one part is kind of done, other part is unknown to us. Okay, so shall we go forward? Okay, so now how to calculate in practice, T rho of R, the kinetic energy. So that is where a fantastic paper of Kohn and Sham comes. And, as you know, most of you, I think, whoever has used density functional theory would have used the Kohn-Sham formalism of density functional theory. Okay. Now, what is so exciting about this great paper? Okay. It's 1965. Okay. So the way that this paper talks about is that if you have n number of electrons, they are not interacting with each other. Okay, then you can define what is called a Slater determinant. Okay, as the wave function of n particles that are not interacting. Because we have n number of electrons in our system, we know they are interacting, but let's for the moment assume that they are not interacting. Then the wave function of those quantum mechanical objects, quantum mechanical n particles, can be written in terms of what is called a Slater determinant. I'm not going into the details. Okay, so if that is the case, for such a system, non-interacting system, kinetic energy is trivial. Okay, it's straightforward. It is simply this expression. I don't know, many of you might have done particle in a box problem. This is the kinetic energy that you have evaluated for particle in a box problem, which is a non-interacting system, right? So this is exactly identical to particle in a box problem. You just need to calculate the kinetic energy using this integral. Of course, this is the second derivative. Okay, this is the second derivative of this function. Whatever is that wave function is, you have to calculate the second derivative, right? So of course, you need to know these one electron or one particle functions, right? I mean, and these one particle functions are in fact required for you to create this, Slater determinant. So this is the total wave function of n particle system. which is written as a Slater determinant of many one electron function. These are not simple products of one electron function. These are asymmetric products. Okay, that's why this product is calculated using the Slater determinant. This is some special product which follows certain rules which are required for quantum mechanics. So this, once you set it up, and this is very simple to set it up, I can calculate the total kinetic energy of non-interacting system, provided you tell me what is the one electron function. So if I know the one electron functions for n particles in my system, and I assume that these n particles are not interacting, for me particles means electrons, I can calculate the kinetic energy. Okay, so I'm going to call these one electron functions as spin orbitals. Orbitals means orbital is actually one electron wave function. Spin orbital is means it's not only having the positions, but also it depends on the spins, because electrons are quantum mechanical objects. We need to also handle their spins. So these are spin orbitals. So these are wave function, which is a function of not only the x and y and z, but also whether it is alpha spin or the beta spin. Okay, it will also depends on the spin of these particles. Okay, so well, I mean, this is nice way of approximately calculating the kinetic energy, provided I know this. Okay, and of course I need to correct all these approximations also, right? If I treat all the n electrons in my molecular system non-interacting, then I can calculate, use this equation to calculate it. But how will I get this? Okay, so that is where that is where the whole business of quantum equation comes in. So let's assume you have n electrons in your system, and let's assume you approximate the Hamiltonian operator of this system, this n electron system, using the Hamiltonian operator that you are seeing here. So what is this? This is simply the kinetic energy, like a particle in a box problem. Okay, but on the top of it, you are adding an additional potential, okay, some effective potential. Okay, so now you see this is simply these are simply like one electron potentials, right? I mean, this depends on this I mean, this sounds so it is an effective potential. So this is a problem that you can actually solve. Okay, I mean, some of you might have already solved such problems when you have done the basics of quantum mechanics. So this is a problem that you can handle. Okay, but this is just a hypothetical system for my n electrons in my molecular system. Okay, so we are going to construct this external potential in a manner that there is no electron-electron interaction. And when there is no electron-electron interaction, this is a problem that can be solved very easily. Okay, Hi equal to E psi is a problem that can be solved very easily, provided there are no electron-electron interactions present. Okay, but I mean, of course, this is a fictitious system. This such a system will exist or not. I mean, it's not very obvious, right? And very interestingly, uh, so this is what this is a little bit of math which I'm not really going into the details. Let's assume there is such a fictitious system present for all our n particles in our system, and the solution of this for the Schrodinger equation for with this Hamiltonian operator is this psi. Okay, psi ks. This is let's assume the solution, which means I have h of s acting on the psi will give you e times the psi ks. So that's the kind of a solution that I'm looking for. Okay, now if that is the case, okay, and I can actually, if because this is like a solvable problem, this is actually like a one electron Schrodinger like problem, where you can show that there is an effective operator, one electron operator operating on each of these orbitals, gives you the corresponding eigenvalue and the orbital back, the wave function back. Okay, so this is a feature of this non-interacting system. Okay, so this is very typical of like if you would have solved particle in a box problem, n particle non-interacting problem. Okay, you will find the same kind of equations coming here. Each particle can be solved separately. So same thing here, you have n number of particles, each of them will obey a Schrodinger equation like equation, and which can be solved very easily using mathematics. Okay. So what is this operator? This it turned out this operator, this one electron operator, is nothing other than the operator that we just now saw, the kinetic energy of that particle and the effective potential energy acting on that particular particle Ri. No electron-electron interaction. So it doesn't, the ith equation will not depend on J. All these set of I equation for I equal to 1, I equal to 2, I equal to 3, they don't really care about what that a second electron is doing. Okay, as you know, that is not the right thing to do, but we are just going to assume this is what that situation is. Okay. Okay, so this is something something kind of just we came to this separately, making a major assumption that these n number of electrons are not interacting and trying to get to these equations. Okay, now the question is, how do we connect whatever we just now solved to the actual system? Because unless we make a connection between this to that, there is no point in discussing this at all, right? Of course, you know that there are n number of non-interacting particles. You can solve like a one electron Schrodinger like equation, which you already know, or somebody knows how to solve it. Okay, but we don't know how to solve the n interacting electronic system, and that's actually the business, right? And that's actually the problem we are talking about, right? So what is the relationship of this to that? So first of all, we assume that this external potential is such that we are going to get the density of the actual system from the density you calculate from this one electron function. Okay, so we're going to say that let's assume that this potential, effective potential acting on each of these electrons, which we introduced in the previous equation, is such that the one electron solutions that we get from this Schrodinger equation, you square them and sum over all these orbitals, you will get the electron density of the actual interacting system. See, in the left hand side of this equation is the density of the fictitious system, but the density of the fictitious system is made to be exactly identical to that of the density of the actual system. Okay. If this is possible, the kinetic energy is straightforward calculatable, okay, using this one electron function. But of course, we know this is not the right kinetic energy. It's an approximate kinetic energy. Okay, and of course, we know we can calculate the electron-electron interaction, like I discussed to you earlier. But that's also simple. Okay, now that we know the electron density from this one electron function, we can calculate with the one electron function the kinetic energy. From the density, we can calculate the electron-electron interaction, and of course, we can calculate the nucleus electron interaction exactly correctly. Like I mean here, this one here, right, in the green color, right? So that is exactly correctly. So there is no need to discuss about it further. So with the availability of these one electron functions, I can approximately calculate the kinetic energy. I can approximately calculate the electron-electron interaction. But as I told you, they are not exactly correct. Okay, so we need to introduce some corrections, and that's what you are going to see here. That these corrections, we need to introduce some kind of a correction. This is the fictitious kinetic energy that we introduced using the one electron function, but the actual one was this. Let's assume we know the actual one. Then this difference is the residual kinetic energy, which is the correction that we need to add to the total energy. Electron-electron interaction, we know this exact electron-electron interaction we are not going to get. We are going to get only this approximate electron-electron interaction. So the difference is the correction. So these two corrections should be added to get the total corrections that we need to add to the total energy. And this is what we call as exchange correlation functional. Okay. This exchange correlation functional is also a functional. We hope to express this in terms of the density. Of course, nobody knows what this functional is, the exact functional form is, because we do not know what is T. we do not know what is VEE. So without knowing it, of course, there is no way that we can calculate the exact correction. But let's assume that we have some way to get close to what exact exchange sorry, these corrections are. So therefore, we assume that, okay, I mean, this entire thing can be somehow calculated as a functional of density. And so therefore, we incorporate this entire correction as exchange correlation functional. Okay. So therefore, the total energy now will have the kinetic energy. You can see here, this is the kinetic energy we calculated approximately. This is the Coulombic interaction that we calculated, electron-electron interaction, calculated as a Coulombic interaction over density, which is approximate. This is the correction that we have added to the mistake that we do here and here, okay, which is exchange correlation. We hope to get that also as a functional of density. And of course, the nuclear electron interaction, which we already know, it's very clean. There is no approximation involved. Okay. Now, one small mathematical point is that since density is sum of square of all the one electron functions, I can rewrite this entire expression in terms of, you can see I can introduce or rewrite this entire equation over the one electron function. You see that one electron functions here, 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 okay? And of course, I'm not discussing this right now, okay? So all of these are now written in terms of one electron functions. Now, the beauty is we earlier showed that in Hohenberg and Kohn said that the energy functional is variational to density. The same thing we can now extend to one electron function, the orbitals that we introduced for the non-interacting system. We can say that, oh, now the energy will now change variationally also with respect to this one electron function. Okay, and of course it has to follow certain constraints like orthonormalities, etc., etc. But otherwise, if you change psi, like in in a typical Hartree-Fock kind of equation, you can actually vary psi and try to minimize the total energy E. Okay, so which means we can use a steepest descent algorithm, because now you can calculate the derivative of E with respect to psi, right? I mean, because this is an energy functional, which is a functional over psi. So I can say I'm changing psi. Okay, I'm changing psi. Then I can calculate the gradient, and you can see this is the gradient. Okay, this is the gradient, which is simply the functional derivative of the previous equation. I will be able to predict the new value of the psi. What is psi or the phi? That is simply the one electron function. So I can predict the minimum, so basically the value of the function, the wave function for which the functional is lowest in energy, because I know the gradient. I can calculate the gradient because I have an expression in terms of psi using a simple minimization algorithm, for example, a steepest descent algorithm. Okay, so this is the current assumption of the wave function. I can predict a better wave function just using this. Only thing is I need, this is a parameter, and this is something that I can calculate from the previous equation. So I can keep improving iteratively to the best solution for the quantum equation. Okay, so this is the gradient minimization. So I'm not going into the details, and actually this gives you an equation like this. And this equation actually is nothing other than the quantum equation. And if you actually look closer, you get a one electron Schrodinger equation. You can see that there is a kinetic energy that you calculate over one orbital, and this is, so to say, the effective potential that you have again is a function of only one coordinate, and that's exactly the quantum equation that you actually looked at earlier. And these epsilon I is the orbital energy. Again, this is a mathematical derivation that one could do. For example, in my course, I would do this, but now we don't have time, so we'll skip this. So now the only tricky thing that you need to think about is that, well, this one electron potential that you talk about for solving this one electron Schrodinger equation, is dependent on the electron density, right? And this is simply coming from the fact that you have this rho of R1, rho of R2 by R12. That term, okay, introduces this rho of R2 as requirement of having rho of R2 in computing this one electron function, okay, one electron potential, right? So that means unless you know the density, you can't calculate the effective potential for the one electron Schrodinger equation. And unless you know it, you can't solve it to get the one electron wave function. And unless you have the one electron wave function, you can't calculate the density. Okay, so it's like a chicken and egg problem. So what we actually have to do is to do a self-consistent field calculation. What we do is something like this. We guess the one electron wave function, Born-Sham wave functions, okay, and independent non-interacting system wave function, from which you know what is the density, okay, from which you can calculate the energy that we just now discussed, okay, and then let's forget about this. Then of course, once you know the density, you can calculate the one electron potential energy, like I showed you in the previous slide. Once you know the potential, you can solve the one electron wave function, like I showed in the previous slide, okay, and that gives you a new set of orbitals as a solution to this one electron function, okay? Now, so you are getting a new set of one electron functions. This new set of one electron functions gives you the new density, and which gives you new energy, and you can keep on iterating it till you see there is a convergence in the energy. That means the currently predicted energy is actually almost close to the one that you predicted earlier. Okay? Now, why you need to solve this in iterative fashion? Because your this one electron potential that you have depends on the density. Okay, so if you actually give a very good guess of the density, your potential is nearly the same as that of the previous or the actual solution, which means you need only few steps of iteration. Okay, so there are a lot of tricks people use today to improve the prediction of density or improve the prediction of one electron potential, which includes also the machine learning based techniques, or there are interpolation based techniques which will actually speed up these iterative procedures. Okay, so typically you need sometimes tens, several times, sometimes you need hundreds of steps to iterate to get to the right one electron functions, and therefore the electronic density. Okay, so that you will see also, you will also see this in your when you start running the AMDKIIT code, you will actually see these kinds of iterative procedures, and Dr. Paramita Ghosh will actually point you out on this particular slide, because that's exactly what we are solving in AMDKIIT. Very quickly, to just tell you this functionals, there are a lot of these exchange correlation functionals are available, and as I told you, that these exchange correlation functionals are actually correcting the error that you have made in building the on solving the otherwise you are when you solve the quantum equations. So there are various variants of it, and and depending on the quality, we can think of these different ladders of exchange correlation functionals. For example, you have your generalized gradient approximation, you have local density approximation, you have hybrid functionals, you have meta GGA functionals, you have um, uh, so we have different category of these functionals depending on the accuracy. Of course, one sad part is that as you go up in the ladder, although you are getting more and more close to the exact results, the computational cost also increases. So, for example, the hybrid functionals calculations are quite expensive compared to that of a GGA or a meta GGA calculation, or even an LDA calculation. Of course, but the hybrid functionals will offer you much more accurate results that you can confidently believe. Okay. So again, and this is just slides will be shared with you, so I'm not going in detail. So this is simple LDA where you assume some functional form of density for the correction that you need. in typical exchange correlation implementation, exchange and correlation, I mean, the quote unquote exchange and correlation. Again, remember, this is not exact exchange that we are talking about or exact correlation that we are talking about. These are just corrections to the exchange and correlation, using different physical models or empirical models, okay, or sometimes fitting, okay. Because even today we have machine learning helps you to come up with functional forms, okay, which will help you to give you these corrections to the calculations, in a much better manner. So the lowest in the ladder is LDA, local density approximation, but these functionals are no more used, and you can't publish anything with this, unfortunately, because even the structure, the frequency, the properties that you calculate, they're very off. They give results close to the typical Hartree-Fock equations, but as you know, even a typical Hartree-Fock equation results cannot be published today. Nobody is going to believe you. So, I mean, what we generally see is shorter bond lengths. The two atoms will will be more, or the bonds are kind of, the bond lengths are underestimated. So the bond strength is overestimated. So that gives substantial energy, substantial error in predicting the property of the molecular systems. Okay, so we're not going to really do any calculation. I think Dr. Ghosh has also arranged hands-on sessions using better functions than LDA. Then there are these GGA gradient, generalized gradient approximations. Here, you have this exchange and correlation calculated not only using the density, but also the gradient of the density. Okay, so you have a functional of density as well as the gradient of the density. And I'm not showing the equations. It depends on, there are a lot of different types of generalized gradient approximation, depending on who proposed it, for what systems it has proposed. There are various variants, out of which one of the functional which is quite exciting is PBE, the Purdue-Burke Ernst-Hoff functional, which, for example, I use quite a lot even today in my lab. It's quite nice. It's very accurate. It's no parameters involved. Okay. Of course, it's not as accurate as the hybrid functionals. In hybrid functionals, it's more complex. It's not only having LDA, but what we do is actually we also calculate Hartree-Fock. We do a small Hartree-Fock like exact exchange calculation, and we take a percentage of this exact exchange computed using Hartree-Fock to this calculation. Okay, so it's a bit more complicated, and because we need to do a Hartree-Fock kind of an exchange calculation, it becomes, of course, computationally more expensive. But the beauty is that it gives you really good results. Structural properties are wonderful. The energy is wonderful. I mean, even for not only for molecules but also for solids. So it's one of the most demanding functionals. But of course, you have to pay the price for the accuracy because it takes more computing time than a generalized gradient approximation. Typically, people start with GGA, and you pick one of your choice of GGA functionals, then you kind of improve it upon it using hybrid functionals. But if you have better computing resources, you can straight away go for hybrid functionals, or in fact, meta GGA kind of functionals, which is slightly, um, better than the GGA functionals, and then you can show the results. You can use the results on that. Yeah, so in meta GGA, you have got also the kinetic energy is already part of the function. You have the second derivative of the density part of the function, so it's more complex functional. Okay, and so one of the most popular today is scan functional, especially in physics community. A lot of people are using scan functional. There are meta GGA functions with hybrid also added to the top of it, like in chemistry community, Minnesota functionals. Some of the Minnesota functionals are hybrid meta GGA functions. They're pretty good in terms of predicting structure and property. But there are a lot of questions that are being asked in the literature recently. Are these right functionals? Because some of these functionals are not giving the electronic density properly. So there are questions asked by a lot of researchers on, okay, are these still the right functionals to choose? So it's a growing field. It's an ever-changing field. Maybe day to day, a lot of action is happening here. So you should you should review the papers. You should know what is happening in this area so that you pick the right functionals. Maybe what was right a year ago is no more right. So you have to be in the keep updated with this. Okay. So I have some of these reviews given here. You take these slides, go through it, and then uh, I think I really like some of these papers, and of course there are much more. The literature is really vast, but my favorite books and reviews are here. Okay. Okay. So now I think I have got 10 minutes or 15 minutes more. Paramita, is that correct?
Yes, sir. You have time
Yeah.
till 1:30.
Oh, okay. 1:30. Okay. Okay.
Mhm.
So let me quickly go through like how practically we're going to compute these things, right? So as I said, we start with this one electron function. Now we will and we will minimize this one electron function. Okay, so I have that psi is the one electron function that we talked about. Okay, and now we need to minimize the function. That means psi has to be changed, right? Psi is a function in XYZ space, right? Now it has to be changed. So now how will I change the function, right? I mean, that's quite complicated. I mean, I can I can have sine of x maybe as one function. Then I say, okay, now let me not try sine of x. Let me try sine 2 of x. Then somebody says, oh, no, 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 no. Let's try sine x plus sine 3x minus tan x. So function have to be changed, but I don't know how to change the function, right? It's complicated. I mean, mathematically, whatever we just now said is all beautiful, but in computer, how you implement this, right? That's where the basis sets come in. Okay, you can change the function variationally by using the concept of basis sets. And not only that, this gives you a mathematical way of solving the one electron Schrodinger equation in a simple way. You can write a MATLAB code and solve it, as simple as that. Okay. So how do you do this? Very simple. You take your one electron function as a linear combination of known functions. So these known functions are called basis functions. So for example, this is a function phi of k is a function which I know already. Okay. I tell the computer that is sine of x. Okay, I say, okay, I do not know whether it is only sine of x, but it could be sine 2 of x, sine 3 of x, sine 4 of x, cos 2 of x, cos 3 of x. Maybe there are many such functions might be contributing to my actual solution. So let me take a linear combination of all those functions which I think can contribute to my actual solution. Okay? But I don't know how much each of them are contributing, right? So that is why it's called a basis function. They are the basis to the actual solution, but I do not know how much they are contributing. So these are weights added, or these are coefficients, which tells you, okay, 10% of the sine of x, or 20% of the cos of x, or 30% of the tan of x, okay, whatever that is. So that is still not known to me, but I can change this psi. You see that this is unchanged, right? I mean, this is fixed already, but I can now change the psi simply by changing these weights. Okay, so therefore I'm going to take these coefficients as a variational parameter. Now the variational theorem that I already talked about in terms of the one electron function and the density, both can be written in terms of variation with respect to these coefficients C, and therefore whatever I just discussed earlier, okay, we can actually write as, instead of del E by del psi or del E by del rho, I can write del E by del C, which gives you variational theorem. Okay, and you look for a set of coefficients C for which the energy is the lowest. That gives you the ground state energy. Okay. Now what you figure out is that when you do this variational theorem and you look for the minimum for the energy by changing the coefficient, you get into a set of linear equations, and what that you can solve using beautifully using matrix diagonalization techniques. Okay, how do you get this? You actually have to take, for example, a case of I mean, you take Atkins, okay, physical chemistry Atkins. You look for this how H2 plus problem was solved variationally, okay, and that gives you the handle of how matrix diagonalization can help you in solving problems variationally. Okay, so this is problem that you can find in all quantum chemistry books or quantum mechanics books. But even if you take physical chemistry Atkins, you will find this in details. Okay, so it is very trivial for you to realize that, oh, I mean, once you have this variation and you want to implement this variational theorem, you get into a linear set of equations that gives you a direct access to solve those linear equations using matrix diagonalization. So there are various basis sets. So I told you that I can use phi as sine, cos, and so on. Or in fact, I can use a Gaussian, I can use a wavelet, and so on. So there are various basis sets are available today. I mean, this is not complete list. In fact, many of the latest codes or a lot of excitement that happens is also using even Slater function themselves. Okay, so not necessarily any of these functions. So you can have Gaussians, you can have plane waves, you can have wavelets, and and the old Slater functions and so on. So what we will be looking at is just the plane waves. I will tell you what a plane wave is. So that as the basis set, and then try to derive all these equations. That will help you to solve these linear equations that comes. Okay, and in fact that solves essentially that solves this one electron function that we just now talked about, right? Because this is the crux of the problem, right? You need to solve these equations, this one electron Schrodinger equation, right? And for that you simply use you simply use these basis functions. Right? So what is a plane wave basis? Plane wave basis is what you can see here is the plane wave. Okay, this is very simple actually. If you think of this expanding this exponential ig dot r, okay, let's forget about ig dot r. You simply consider ei of x. Okay, so which means ei of x is cos plus I sine of x, right? Cos of x plus I sine of x, which means your basis set, your basis function is simply a sine and a cosine. Okay, which means you are writing your wave function, one electron wave function, as a sum of sines and cosines. Okay. Now, what is this G? G is actually going to tell you what is the frequency of that sine and cosine. Okay. So, for example, you can say sine cos of 2x plus I sine of 2x could be one function basis set. Another basis set could be sine cos 3 of x plus I sine 3 of x. Okay. The next one could be cos 4 of x plus I sine 4 of x. So it is what this G is therefore doing is simply to set the frequency of the sine wave. Okay. And you can in your actual calculation, you can think of having several G's. That means several frequencies. Okay, you can have very high frequency waves, you can have very low frequency waves. So this is nothing other than a Fourier expansion of your unknown function. Okay, very nice. So if you use this function, then you can simply show that you can express the density in terms of the in G space, which means the frequency space, or you can have it in real space. Okay, and all the mathematics is pretty clear. And again, I'm not going into the details about it. Okay, so you have, for example, you have your psi in Cartesian space, right, which you are now writing as a linear combination of sines and cosines of various frequencies. Now you can either work in Cartesian space, you can also work in the frequency space, because the frequencies because you are actually worrying about how each frequency sines and cosines are contributing to your solution. So you can in fact represent your solution also in the frequency space, and that's what you're seeing here, right? You can see this density is expressed in the G space, the frequency space. Psi is expressed in the G space, okay, which is the frequency space. So you have this translation. You can translate from the frequency space, or to the real space means the Cartesian space, and vice versa, simply using this simple mathematics. And this mathematics is nothing other than Fourier transform. Okay, it's a it's a Fourier transform that you need to do to get either in frequency space from real space or Cartesian space, or and vice versa. And all your formulation of calculation of energy can be either done in frequency space or in Cartesian space. So that's the beauty of this. Okay, this is one simple way of doing it. Now, why are we taking plane wave basis? What is so exciting about the plane wave basis? Because it is sine and cosine, it's periodic, right? So, and you've already possibly learned about Fourier transformation, that okay, any periodic function can be beautifully expressed in terms of sines and cosines, right? And as a Fourier expansion, exactly the same thing. So, and if you look at a periodic system like a solid, or if you look at a liquid, they're periodic in space, because they're infinite size. System size can be treated as a periodic system. So therefore you can actually use um, these kinds of basis set to express the density of the molecular system repeated infinitely periodically. Okay, and that's the beauty of this. So because now if you want to look at bulk water, okay, water which is in your glass, okay, or you want to simulate a solid salt, okay, or some other solids, surfaces, interfaces, you can treat using the periodic basis set, because they're periodic, they're large systems, and they have this periodic nature. So you can actually use plane wave basis set ideally. Okay, if you use Gaussian basis set, they're just Gaussian functions, and they finish off, they tail off, right? They are not periodic. So if you are actually looking at a molecular system, you can, and which is not periodic, they are isolated, you can actually go for a Gaussian basis set. Okay, so well, I mean, this is some small point. When you start doing the calculation, you get into some parameters that you need to define. Now, what we do in here in our AMDKIIT, and also in many other plane wave codes, is that we don't take all the frequencies. Okay, because we can, in fact, in the previous equation, you can see that I could take all the frequencies, right? I mean, so here, for example, actually, there is no control on this g. Okay, this sum. I can take sine of x and 2 of x and 3 of x and 4 of x, 5 of x, 6 of x, 7 of x, 8 of x. Where will you stop? Right? You cannot have this sum infinite. If that is the case, your calculation will go crazy, because your calculation will depend on the number of basis functions. More the basis functions, more computing you have to do to do diagonalization to solve the linear equations that comes out of the Constant equations. So you don't want this g to be like infinity. You need to stop at some point, which gives you a confidence that okay, after this, nothing much is contributing. No error is going to really happen. Okay, so you need to terminate this sum at some point. So where will you stop? The typical trick that we use is that we look at the magnitude of g, which is a frequency that I told you, right? So if the square of this g square is less than some number, okay. Now the way that we calculated, we introduced g is this half g square. Will give you in atomic unit and energy unit in atomic unit. So we set a E cut, which is the parameter. If it is less than this, so if half g square is less than the cutoff, then we will consider all the g values, which is going from 0 to whatever value of g will be considered in the calculation if half g square is less than the cutoff, right? Which means something like this, right? So because half g square is something like r square kind of thing, okay, which means it's a circle kind of thing. So in g space, in frequency space, you will think of all these points will be considered for the all these frequencies will be considered for my calculation, because all of them are having a value of G less than the cutoff. Beyond this cutoff, I'm not considering. There are many G values that I'm not considering because I think they are not going to be critical for my calculation. They're not going to introduce any error. Okay. Okay, now the reason why you want to introduce this is simply because you can show that the quantum potential energy in the frequency space, okay, will converge very rapidly with increasing modulus of G, which the value of the G. So therefore, you don't need to really take all the infinite values of the frequencies, but only a few values. Okay, so well, there are a lot of technical details. I'm not going into the details. The number of grid points that you need to hold, or I mean, these are the grid points, right? You can see the grid points, and each of these grid points corresponding to a frequency. Um, so that number of grid points required is related to the cutoff that you are defining. Of course, that's definite, right? I mean, more the energy cutoff, the bigger the circle is. So the number of grid points that you need to consider in your calculation will be higher, right? Because as I told you, that all our calculations will be on grids. Density is on grids. Okay, entire thing is on grid. So therefore, uh, yeah, I mean, the number of grid points that you need to consider in the G space will definitely going to increase with respect to the cutoff that you are defining. And that scales something like this. Okay, so okay, so that defines a number of grid points, and also in your calculation you will see that the number of grid points also depends on fast Fourier transform that we will do. Okay, so because we have to do some fast Fourier transformation to really go from frequency space to Cartesian space and Cartesian space to frequency space. Okay, this is the Fourier transform that you see here is the Fourier transform. And to do this back and forth from G space to R space transformation, I'm going to use fast Fourier transform, and it actually also tells you that what is the optimal size of the grids and so on. So again, I'm not going into the details, but it's just for a completion purpose. I'm telling you that in this AMDKIIT we use this formula to find the optimal value of the grid points. Okay, so now we also use pseudo-potentials. Okay, and pseudo-potentials are important because the wave function, okay, the wave function actually has a nodal character, right? I mean, the atomic orbitals, higher the angular momentum, you get introducing the more number of nodes. More the nodes, the function will become more wiggly, right? So for example, you can see this dotted line here, right? This is the actual 3s wave function. You see there is this wiggle, right? This wiggle. More the wiggles, more number of basis sets you need to introduce. Okay, so for example, to represent these wiggles, okay, you see this wiggle, right? I mean, this wiggle, you need more basis set, but more the basis set, we are in trouble because the linear equation that we need to solve, the size of the problem will increase, so the calculations will become faster actually. Also, there are memory requirements because the matrix that you need to solve becomes very big, so there are issues. Okay. So we introduce what is called pseudo-potentials, and this pseudo-potential replaces these kinds of solutions with another solution where there is no node. Okay, so I mean, this of course it's an approximation, and this approximation actually replaces the nodal character. You see, these nodal characters are gone with the pseudo wave function. It actually smoothens it out. Of course, okay, and you can see after certain distance, you actually get to reproduce this very correctly. Okay, so that means after a certain cutoff, you actually make sure that your pseudo wave functions, pseudo potential that you introduce, okay, will provide you with the right solution, but below a cutoff that it will not give you the right solution. Okay. Now you need to make sure that when you do such an approximation, when you introduce such an approximation, the core charges will be changed. Okay, so you need to introduce certain corrections to avoid errors. So all of those are taken care in what is called a pseudo potential. So you take pseudo potentials to make the calculations fast and more efficient by kind of introducing an non-nodal wave function, but of course take care of the corrections that you need to do at the end. Fortunately, this is shown to not introduce any major errors because you make sure that the valence potential, the valence electrons are feeling the right potential, because you make sure that the wave function of the exact atomic wave function and pseudo wave functions are really mimicking exactly correctly. So, so therefore that helps you really, um, really well. So the cutoff parameter that I talked to you, which is the E cut in my previous slide, that's actually now become a much smaller quantity with a pseudo potential. You can see this is the wave function cutoff, okay, parameter that you introduce in as an energy unit. That number will become small, and less the number of E cut, less number of grid points, and less number of frequencies that you are going to consider, and that saves the computing time. It makes it more efficient, obviously, right? So therefore, potentials are critical for plane wave calculations. It really speeds up the calculations. It gives you, it won't really introduce any major errors. You need to, of course, implement for various type of pseudo potentials, how these corrections have to be introduced. So MDKIT supports a lot of types of pseudo potentials, which Professor Ghosh will, oh, sorry, Dr. Ghosh will be introducing it to you, and she will also tell you like how to access these pseudo potentials. Okay. Well, now to put all these masala into set of equations, the quantum equation, you get this complicated set of equations, but these are simple actually because they can be written on a piece of slide, right? So you can, I mean, the beauty of this plane wave thing is that it's very simple. Final equations to calculate different components of energy become simple, and you can calculate these things sometimes in real space, sometimes in Fourier space, in frequency space. Okay, so you need to implement this, and that's what we did in AMDKIIT. Okay, again, I'm skipping these things. Good thing is that your basis set is now defined by only single one parameter. Okay, and which is the energy cutoff. Okay, unlike in terms of Gaussian basis set, you need to really worry about how many different types of Gaussians that you are considering. What is the width of these Gaussians, whether it is diffusive and non-diffusive, how diffusive it is, and diffusive, etc., etc. So therefore, you need to really be careful with the Gaussian basis set to make sure that the results that you are talking about are the right results. Because your final results are going to get affected by the basis set. The plane wave basis set is ideal for periodic systems because it's beautiful and it's only single parameter dependent. And later I will tell you, like, it is also having no Poulet forces because these plane waves are simple sines and cosine. They're not centered on atoms. So when the atoms are moving, you don't need to worry about the forces coming due to the change in the basis set, because atoms are moving. The basis set also has to move, because if the basis sets are centered on the position of the nucleus, like the case of a Gaussian, and that's not the case for plane waves. So you don't need to worry about those Poulet forces, which is very good for performing molecular dynamic simulations, and it's very important actually. But unfortunately, this is not very good for treating isolated system when you really want to look at one water molecule and not interacting with anything else. That's a difficult. Of course, that you can still do it, but of course you need to. It's these methods are not truly suitable for that. But it is not that it's not possible. For example, Dr. Paramita Ghosh will be doing the isolated system actually, okay, where you will actually model an isolated water molecule. Then she will also help you to solve periodic water molecule, which is naturally a periodic system. Okay. Then of course, the code that can also that you have is also suitable for doing molecular dynamic simulations. Molecular dynamic simulation is pretty easy. This is just classical equation of motion, right? I mean, this is force is equal to mass into acceleration. So you can see mass into acceleration is force. This is the force. And what is this E? E is actually the energy of density from the density functional theory, which we already discussed. You need to calculate the derivative of this energy functional over the nuclear position. That gives you the force acting on this position, on this nuclei, and you use that force to integrate the equations of motion classically. And in the integration of classical equations of motion is something that you already know. Right? Now, what is the beauty? I mean, you actually can simulate the dynamics of atoms in a molecular system like this. This is when you actually integrate the equations of motion, which means you can really see a chemical reaction in the computer. How an atom goes and binds to the other one, bonds are breaking and forming. All of those events can be simulated in computer using this ab initio molecular dynamics simulation. It gives you access to finite temperature, it gives you access to pressure. Okay, so therefore any catalytic reaction can be modeled more realistically using ab initio molecular dynamics, and that's something is already available in AMDKIIT. I guess you'll be also doing that. If not, you can, of course, you can see some of the tutorials, and you can always do this separately also if it is not in the tutorial. So so every time step, so there is a time step. So when you do numerical integration, you actually, you have some coordinates for which you solve the Schrodinger equation. Okay, then you solve the Newton equations of motion, go from t equal to 0 to t equal to delta t, right? And at that point, you get a new set of positions and velocities. From there, you integrate to 2 delta t, 3 delta t, and so on. So each of these times you have to calculate the forces acting on all the atoms, and because you have to calculate the forces acting on each of the atoms, you need to solve the Schrodinger equation. The Schrodinger equation is solved every time step. Okay? In our case, we solve the Kohn-Sham equations, get the energies, and calculate the gradients to get the forces. That's it. Okay. Now, since it is integrating position and velocities, and since I know the velocities, I know the masses, I can calculate half mv square, and that gives you the kinetic energy. And if I know the average kinetic energy, I can calculate the temperature of the system. This is beautiful. Okay, so that means you have direct access to the temperature of the simulation from the information of the position and the velocity. Okay, right. So there are a few things like total energy is conserved and so on. I'm skipping those things. Okay. So how do you integrate equations of motion? I'm skipping that as well. This is simple integration of something like a Newton update kind of equations. So I'm skipping that. So as I told you that you need self-consistent field calculation, which means you have to solve the Kohn-Sham equations at every time step. Okay, and that's important. So every time step will require one self-consistent field calculation, and that's critical. Okay. Okay. Okay, I'll skip this also because of the time. Of course, you can really look at complicated chemical reactions. So this is a reaction which is like hydrolysis of a formamide in water. What you do is you actually, so a chemist will approach you that, okay, I want to know the energetics and want to know what is the energetics of this reaction, what is the mechanism of this reaction. Okay, what you do is I mean, the experimentalist will tell you that this reaction happens in basic water. So you can set up such a basic water system in a periodic box with water molecules and the reactants, and you can use techniques to simulate chemical reactions in molecular dynamics, and you can calculate energies. Okay, and you can calculate energies, and you can see how confident you are with these energy predictions by running long simulations and things like that, and you can calculate energy landscapes. Okay, so that's the power of molecular dynamics. Okay, so there are many things that you can do. Like you can look at catalytic cycle. You can actually look at surface reactions. So this is for example a high temperature, high pressure reaction that we simulated quite some time back on a mineral surface. So these kinds of systems can be easily set up in the computer, and these techniques are really ideal for looking at such a reaction. So this reaction was interesting. This was a reaction where we were looking at peptide bonds formation in primordial condition, right? before the human beings were formed, there were volcanoes, and near the volcanoes, how the peptides could have been formed. So we predicted that using this ab initio molecular dynamics simulation, or molecular dynamics simulations using density function theory. We could look at single atom catalysis. We can look at even more complex things like how electrons are, diffusing, or electron localization is changing as the finite temperature effects are coming. We can simulate those for molecular dynamics, and also for the plane wave basis set. I recommend this book. There are free. If you don't have access to this book, you can click on this link, which gives you free. These are free PDF files available online, which gives you also fundamentals of plane wave theory and ab initio molecular dynamics. Okay. By the way, ab initio molecular dynamics simply means molecular dynamics using, quantum mechanical forces, right? Which means you're having your atoms moving classically, but when you predict the classical motion, you need to have the forces on atoms, and these forces are calculated by solving Schrodinger equation or using density function theory. Just very quickly, I think this is something Paramita Ghosh will be introducing to you. So this AMDKIIT is a plane wave code. It can do Born-Oppenheimer. In the next version, which we will be releasing, there will be a lot of new features, which will be able to actually perform molecular dynamics simulations, really fast, at much better than any other codes available today. But that's right now not available to you, but that will be soon be made available. And there will be, it can, as I told you, there are different pseudo-potentials. You can use these different types of pseudo-potentials. You can have supercells treated with different symmetry. You can do structure optimization and very simple, input file. Input file is very nice and simple. You have, it's like human readable input file, and there are manuals which tells you like what is the way in which you should build the input files. Okay. So I think this is something Paramita will be introducing you. So I think I will skip this, how AMDKIIT has to be compiled, and how to get the pseudo potentials. Right, Paramita? I think you are going to talk about this.
Yes, sir.
Yeah. So I'll skip this. So for any of these atoms in the periodic table, you can download the pseudo potential from freely from available reliable sources. You can use it with AMDKIIT. Okay. Yeah. So in the future edition, we hope to give you a code which will be able to do hybrid functional calculations almost 140 times, 150 times faster on many of these NSM param machines. Okay. I think with this I will stop, and I